Alright, in this section of Thermo, we're looking at calorimetry. And calorimetry takes our Q equals MCAT equation one step further. Okay. Our first thing we'll look at, if we can get the slides to go, is that the basic concept is heat lost equals heat gained. So in this case, we're talking about like adding, let's say just you've got a pot of or a glass of water. Okay. You drop a hot piece of metal in it, and this is an example we'll look at. Okay, so if this piece of metal is hot and this is water is at room temperature or whatever, we're going to look at what final temperature that would come to. Later on, we'll get into the study like if we put an ice cube in there, right? How cold can we get this container of ice? That's a little bit later. Our first step is looking at things that are in that will not change phases. So the water is going to stay water, and this piece of metal would stay solid in this example. Okay, so we also know that heat lost, heat gained is Q of the hot, and we see the negative sign. The negative sign, remember by convention that negative means that the energy Q is flowing out. Okay, so the hot thing that we have is going to lose energy, while the cold thing is going to gain energy. So in this example, again, we have cold water in here, hot metal. Okay, so we would expect, and what will happen is that when we put the piece of hot metal in the cold water, the metal is going to get colder and the water is going to get warmer. Okay, so that's why we have the negative sign here for the hot and the positive for the cold. All right, energy is going to flow from the hot to the cold. Okay, well, we already have equation to solve for Q. Right, so we can simply set that in. It looks a little bit confusing with all these subscripts of hot, hot, hot. I just included them to make it a little bit more clear. And then cold, cold, cold on the right. As long as you keep both sides straight, you don't have to keep writing that. But again, the negative sign is important because of the convention of heat flow. Okay, so if we take a look at a sample problem, okay, I kept the Q equation up there, but we say a piece of copper at 90 degrees Celsius is dropped into 125 grams of water at 20 degrees Celsius. Final temperature of the water in the copper is 26 degrees Celsius. Okay, this is important in calorimetry, right? The final temperature is going to be the same, right? In almost all cases, right? You put a piece of metal into a glass of water, you expect the temperature of the copper to go down, the temperature of the water to go up, and both end up at the same temperature. Okay. Here we're looking to find the mass of the piece of copper that we put in. So we don't know what size it was. We knew what temperature it was. We knew the mass of it, or the mass of the water, but we didn't know the mass of the copper. So we're going to solve our Q equals MCAT. Oops. So we'll scratch that. We'll go Q. So our negative MCAT, MC delta T. Okay, this is going to be our hot side, equals MC delta T, if I could write, on the cold side. And this will be our water, okay, in this problem. Water doesn't always have to be cold, and the metal doesn't always have to be hot. It could be flipped around. So in this case, the copper is going to be hot. And you could also solve this problem if you had two samples of water. You poured like one glass of water into another. Or the same concept, you want to get the water temperature right in the bathtub, you have to have a certain mass of water of one temperature versus the other. But let's get back to this problem. Well, now we just plug in. Right? We've got the mass of copper, which we don't know, the specific heat of copper, was given to us above at 0.385. Okay, again, that's joules per gram Kelvin. Again, degree C could be plugged in, as those are interchangeable in when you're using delta T. Our delta T in this case, remember, delta T is T final, which was 26 minus the 90. Okay, and this becomes important. Oops. With this final minus initial gives us the negative. Our negative is going to cancel out with the negative sign over there. Then we have the water side. We have 125 grams of water. I think I'm going to run out of space here, but let's keep going. Our specific heat, remember, water is 4.184 joules. Okay, we want to keep it in joules, so it's joules per gram, degree C or K. And then our delta T, okay, the T final is 26 minus 20, and those are in degree C. And I did run out of space. Anyway, if we take an intermediate step, we would have negative M times negative 24.64, and we notice the C again is equivalent to the K, so we're left with joules per gram. It's going to equal 3,138 joules. You notice the negative and the negatives cancel to make that positive. We divide both sides by 24.64 joules per gram, and we end up with 127 grams. And again, that is for the copper. And that is calorimetry problems. You can see where we could solve for any of these values. We could solve for the final temperature. It's slightly more tricky to keep track of the numbers, but it's a common problem that you may run into. But just keep track of all your multiplication and your signs, and everything should work.